Greetings, everyone,
I hope you are well.
and that life is moving smoothly for all of you watching. Today we explore,
A fascinating subject.
in modern cosmology, the cosmic inflation theory. To understand inflation, we first need to step back to the very beginning of our universe. Scientists believe that everything we see today, from stars to galaxies to the very atoms in our bodies, once existed in an unimaginably small, dense and hot state. This early stage is what we often call the Big Bang. But there was a question:
How did the universe
expand so quickly and yet remain so smooth?
and uniform in all directions?
If we only consider the standard Big Bang model, it cannot fully explain why the cosmic microwave background, the faint glow of ancient light still observable today, looks almost identical.
No matter where we look in the sky,
This is where the idea of inflation enters. In the late 1970s and early 1980s, a physicist named Alan Guth proposed that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. To give a sense of scale, during this inflationary moment, space itself grew.
at a rate faster than light.
This does not violate physics, because it is space expanding, not objects moving through space. This rapid stretching would explain why distant regions of the universe appear so uniform. They were once very close together before inflation pushed them apart. It also helps explain why the geometry of the universe appears flat, rather than curved or distorted. Before we move to our today, I want to say that this channel is user-friendly, no offensive content.
No misinformation.
We explain things with respect, curiosity, and authenticity. The beauty of inflation theory is that it connects physics, mathematics,
And observation.
It offers a way to answer long-standing puzzles about the universe using ideas drawn from quantum fields and high-energy physics. It is not just abstract theory. It is supported by evidence found later, which we will explore.
As we continue,
Now that we understand what cosmic inflation means, let us explore how scientists began to test and strengthen this idea. In the early 1980s, Alan Guth's original model had a few problems, such as how the inflationary field could transition smoothly to create the universe we observe today. Soon after, other physicists like André Linde, Andreas Albrecht,
and Paul Steinhardt
refined the theory into what is known as new inflation and later chaotic inflation. These models suggested that a special kind of energy field called the inflaton field was responsible for the rapid expansion. The inflaton acted like a stretched spring, holding potential energy. When released, that energy drove inflation and later decayed, producing the particles and radiation that filled the young universe. But how do we know if such an invisible process?
really took place.
The strongest evidence comes from the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson. This faint afterglow of the Big Bang carries tiny variations, temperature fluctuations, so small they are less than 1 part in 100,000. Inflation predicts exactly this kind of pattern. The rapid stretching of space would take tiny quantum fluctuations
And blow them up.
to cosmic scales. These fluctuations later became the seeds of galaxies, clusters, and all large-scale structure. In 1992, the COBE satellite provided the first map of these subtle variations.
Later,
The WMAP mission in the 2000s and the Planck satellite in 2013
measured them with extraordinary detail.
The data revealed that the patterns matched the predictions of inflationary theory. The universe is indeed astonishingly uniform, but with just the right amount of tiny imperfections needed to form stars and galaxies. Another important clue is that the universe appears flat. Its geometry does not curve inward like a sphere or outward like a saddle. Inflation naturally explains this, because rapid expansion would stretch space until it looked almost perfectly flat, just as blowing up a balloon makes a small patch appear smooth. Thus, inflation provides a powerful solution to three puzzles at once: the horizon problem, the flatness problem, and the monopole problem, which deals with hypothetical particles that inflation dilutes away. By addressing these mysteries, inflation transformed cosmology itself. It gave scientists
A deeper understanding of how something so vast
could emerge from something so small. As cosmic inflation gained recognition, it sparked new questions, not just about our own universe, but about the very nature
of reality itself.
One of the most striking consequences of inflation theory is the possibility of a multiverse. How does this idea emerge? In many versions of inflation, the expansion does not stop everywhere.
At the same time,
Instead, some regions of space finish inflating and form bubble universes, while other regions continue expanding. This process, sometimes called eternal inflation, suggests that our universe might be only one bubble among countless others. Each bubble could have different physical properties, different laws of physics, and maybe even different kinds of matter. Now, it is important to note the multiverse remains speculative. We cannot observe other universes directly, but mathematically, it is a natural outcome
of certain inflationary models.
Beyond the multiverse idea, inflation also connects deeply to quantum mechanics. During the inflationary phase, tiny quantum fluctuations were stretched to astronomical sizes. This means the origin of galaxies, stars, and even the planets we live on can be traced back to microscopic quantum ripples from the earliest instant of time. It is astonishing to think that quantum uncertainty,
The randomness
inside the subatomic world,
laid down the blueprint
for the cosmic web of galaxies we see in the night sky. Scientists continue testing these predictions. For example, one major target is the search for primordial gravitational waves. These are ripples in space-time itself, which inflation should have produced as it expanded at unimaginable speed. Gravitational waves from inflation would leave a unique imprint on the polarization pattern of the cosmic microwave background. In 2014, an experiment in Antarctica called BICEP-2 reported hints of this signal, but later analysis showed
that much of it
was due to interstellar dust. Still, the search goes on.
Future missions,
such as advanced ground telescopes and proposed space observatories, aim to push sensitivity further to confirm or rule out this crucial prediction. Another fascinating aspect is how inflation relates to particle physics. The inflaton field, if it exists, could be tied to physics beyond the standard model. It may involve energies so high that we cannot recreate them even in the most powerful accelerators like the Large Hadron Collider. Thus, inflation sits at the intersection of cosmology and fundamental physics, a bridge between the largest scales of the universe and the smallest scales of quantum reality. This is why inflation is not just a theory
about the past.
It is also a window into the ultimate laws of nature. As we reach the final part of our exploration of cosmic inflation, let us reflect on its significance for both science and human curiosity. The inflationary model
is not only about
explaining uniformity or flatness. It reshapes our understanding
of origins themselves.
It shows us that the universe we live in
may have grown
from something smaller than a proton to larger than all galaxies combined in less than a blink of an eye. This realization forces us to ask, why does the universe exist in such a way that life can emerge? Why are the laws of physics so finely tuned Inflation does not answer all of these questions, but it offers a framework
where these mysteries
can be studied scientifically
rather than left
as unapproachable puzzles. Ongoing research continues to refine the details. Some physicists explore
alternative models
like bouncing cosmologies or modifications of gravity. Others investigate whether inflation can be connected to string theory, supersymmetry, or dark energy. What is certain is this: inflation remains the leading explanation for the earliest moment of cosmic history. It explains the large-scale structure, the cosmic microwave background, and the flatness of space with remarkable accuracy. And though challenges remain, its predictions have stood up to decades of testing and measurement. All the information we provide comes from verified historical sources, including books, records, and archaeology. For this topic, the main sources include Alan Guth's original paper, Inflationary Universe, a Possible Solution to the Horizon and Flatness Problems, Physical Review D, 1981. Andre Linde's works on new and chaotic inflation in the 1980s, observational results from the COBE satellite, 1992, WMAP mission 2001-2010, and Planck mission 2013. NASA official resources on cosmology, particularly the cosmic microwave background, publications by the Kavli Institute for the physics and mathematics of the universe. Together, these provide a strong foundation for the ideas shared here. If you enjoyed learning about cosmic inflation today, please remember to like this video, share it with friends,
and subscribe
to our channel, Thrones of Knowledge. And do not forget to press the bell icon so you get notified on time whenever we release a new explanation. Also, we welcome your suggestions for future topics.
Leave them in the comments below
so we can continue this journey of knowledge together.